Hello, and welcome to the Metabolic Classroom. I am Professor Ben Bickman, a biomedical scientist and professor of cell biology. Thanks for joining me for the episode today for this lesson. In today's lesson, we're going to be discussing the confluence of two metabolic epidemics, each in their own right, a substantial problem, and when combined, the problem is multiplied, and that is sarcopenic obesity. Now, let's tease that apart. Sarcopenic obesity is a single problem. But as I mentioned, there are two problems in there, and you can hear them. So sedentary, total bed rest, for example, all of those can be instances or causes rather of losing muscle mass. And then, of course, the obesity part of this problem is obvious, not only to the eye, but to the brain, where you understand what obesity is. It's simply when the body has accumulated too much fat mass. Now, we're going to touch on that in a little more detail, as I have discussed before. As much as we implicate body fat as being problematic or causal to metabolic problems like insulin resistance, it's not the mass of the fat that matters most, but rather the size of each individual fat cell. So there's a little bit of nuance there, and we're going to discuss that, of course. We'll highlight that during the lesson today. Okay, so you know what sarcopenic obesity is. It is the body that is both getting excessively fat while losing its lean mass. This is estimated in a study by Gao et al. 2021, and this will be in the show notes that you can find. It's estimated that within older adults, this is affecting over 10%. So not an inconsequential number of people have this happening worldwide. And of course, as we continue as a population to live quite long and metabolic disturbances are starting earlier in life, and the relevance of that will be discussed soon as an origin of sarcopenic obesity, it's no surprise and fully expected that these numbers are going to continue to go up. Now, one thing that makes sarcopenic obesity unique is that it's not, why is it less common than just straight up obesity, for example, is that normally as a person gains weight, as they go from lean to obese, yes, they are very obviously gaining fat mass, but they also are less obviously gaining muscle mass. After all, every act of living now requires meets more resistance than it did before the person had gained such a substantial amount of fat mass. So the very act of getting up and moving around, let alone climbing a flight of stairs or going on a walk or anything longer, the muscles are challenged more. And thus, very typically, like I said, the same person who is obese tends to have more muscle mass than their leaner counterpart. So then we would just call that problem obesity, and there's no sarcopenia there. So it's the sarcopenia part that makes this less common. It's not uncommon for someone to be overweight or obese. It is much less common for someone to have sarcopenia. Again, it's typically in those three states I mentioned earlier. The very aged among us, or the diseased, or the very related to this, disuse, the people under like true bed rest or very near total bed rest. So very, very sedentary people. They're going to be the ones who experience the sarcopenia. Sarcopenic obesity is likely going to continue to be a topic of conversation just because of, in part, what all of the societal lockdowns caused, where you did have a lot of people, particularly younger people, who had suddenly become more sedentary than they had ever been, and at home more than they'd ever been, where most people tend to snack more and just eat junk food. So what is the relevance of muscle in this? Because the loss of muscle, as we're going to discuss in a moment, really ends up compounding this problem. Muscle is the main consumer of blood glucose or blood sugar. And in fact, it's not even close. So when you eat a meal, and let's imagine you were wearing a continuous glucose monitor, and you see that glucose come up and then come down. 80% of that drop in blood glucose is because of what's going into muscle. So muscle is by far the main consumer of blood glucose. It is eating the lion's share of all of the glucose. So if you start to lose muscle mass, you have lost your greatest glucose consumer. You're losing your greatest glucose consumer. And thus it's no surprise that with a drop in muscle mass comes a substantial drop in the ability of the person to control their glucose. So the drop in muscle is leading to a rise in blood glucose levels, certainly a much longer time in turning the glucose back down to normal after we've spiked it. Now, independent of related, certainly, but still independent of this phenomenon is the direct effect of muscle disuse on insulin resistance. Now, no surprise, of course, you who are tuning into the Metabolic Classroom, I'm very much going to direct a lot of this conversation on insulin resistance. So a study by Dirks et al., 2016, link in the show notes, found that just 1 week of bed rest led to a significant reduction in muscle mass, so significant atrophy. And this is in young, healthy men, like college-aged men. These are going to be the most metabolically robust of all of us. Even still, 1 week of bed rest resulted in a significant atrophy and about a 30% reduction in insulin sensitivity. Isn't that remarkable? So they became 30%, if you will, more insulin resistant after just 1 week of bed rest. And these are in young, healthy, college-aged males. These are bodies that are more inclined than anybody on the planet to keep their muscle mass. And yet even they had not only a significant drop in muscle mass, but a profound increase, 30% increase in insulin resistance measured at the whole body. So pretty significant. Now, I actually, just as a little tangent, although we're going to revisit this inflammation idea in a moment, I was a co-author on a paper that was published from Micah Drummond's lab. Drummond is the senior author from the University of Utah, finding that bed rest was causing insulin resistance in part through an increase in ceramides, which is the lipotoxic intermediate that is causing insulin resistance within the cells of the body. So the bed rest increased ceramides, and when ceramides were blocked, it mitigated some of the insulin resistance of the bed rest. Now, so that's muscle. So I want you to be thinking of muscle because it is just so relevant in our understanding of sarcopenic obesity. And remember, it's the sarcopenic part that is invoking the muscle in particular. Sarcopenia is the loss of muscle mass and strength. So what are some of the causes of sarcopenic obesity? Of course, poor diet with aging is absolutely going to cause this. This is why so many people with sarcopenic obesity are in the later part of their life. It's natural to start losing muscle mass with age. It's also natural as we become more sedentary and insulin resistant with age that we start to promote more more adipose growth. Sedentary lifestyle compounds this. Chronic diseases can contribute to this, but let's focus on the metabolic origins, namely insulin resistance. And because I'm such a thorough professor and scientist on this topic, we're going to look at this in a two-direction manner, because this becomes somewhat circular, where not only does insulin resistance contribute to sarcopenic obesity by affecting both muscle metabolism and fat cell metabolism, but sarcopenic obesity also begins to contribute to insulin resistance, or can directly contribute to insulin resistance. So each of these instances, and through mechanisms we'll talk about, so each of these can be its own origin. So again, sarcopenic obesity can be a consequence of insulin resistance, but it can also cause insulin resistance. So the true causality here can become a little murky. We'll start with the one that I think is more likely, which is that insulin resistance is causing sarcopenic obesity. So let's firstly start with this first mechanism within this pathway, within this line of thinking, the directionality being insulin resistance first, and then sarcopenic obesity being the consequence of this. So the first mechanism is going to be an impaired muscle protein status. Now, insulin is misunderstood when it comes to its effect on muscle protein synthesis. There are myriad published reports that find insulin is not necessary for muscle protein synthesis. So when you think about the protein in a muscle, or all of the proteins, it's the proteins that not only give the muscle its size. More muscle protein means a larger muscle cell, and collectively larger muscle cells mean that the whole muscle is bigger. But where there are more proteins within a muscle, there's typically going to be greater strength and power, which of course is essential for aging well and just healthy health span in general. Muscle mass is one of the greatest predictors of longevity and health span. So just living a long, capable, independent life. Now, again, there's a mistaken thought here. The thought being that insulin is anabolic, that it is directly stimulating muscle protein synthesis. A study by Sri Nair's group, study by Tessari et al. In 86, or Gelfand and Barrett in 87, links in the show notes. They find conclusively, human studies, that insulin, rather than contributing to muscle growth by stimulating the muscle growth side of it, in other words, insulin is not anabolic by stimulating the synthesis of the muscle protein, but rather it contributes to this anabolic milieu within the muscle by inhibiting the breakdown of the muscle protein, a phenomenon referred to as proteolysis. So rather than, again, I'm going to state that again, rather than insulin contributing to muscle growth because it's directly stimulating the growth of the muscle protein synthesis, which does not appear to be the case, insulin contributes to muscle growth by inhibiting the breakdown of the muscle. All right, so for more details, certainly click on the links in the show notes of these papers. So insulin, rather than saying that it's anabolic at muscle, we would say that it is anti-catabolic. Insulin inhibits proteolysis. That's its main mechanism of contributing to muscle growth. Now, that begs the question, why is insulin a drug that is abused, a hormone that is abused as a drug in, say, bodybuilders? I would argue that it shouldn't be. This could be why, just as a tangent, this could be why the body type of bodybuilders has changed so much, almost grotesquely, compared to the bodybuilders of the 80s, whereas they have all been on anabolic steroids, like testosterone and its related molecules. What is new are the hormones like insulin and human growth hormone, which, while they may help with some degree of muscle growth, or in insulin's case, help with muscle growth by blocking the muscle breakdown, it also can be promoting the growth of other stuff like visceral fat or liver growth, et cetera. So growing the soft tissues in the abdomen or visceral space. So just to put a fine point on that and finish it, it's these guys who are not only yoked with muscle everywhere where you'd expect it, but they also have these oddly and almost, like I said, grotesquely protruding bellies. It's because their hormonal cocktail has changed in a way that I think is ridiculous. Just to finish that up, and bring it back to insulin resistance. So insulin helps with muscle growth because it is anti-catabolic. It inhibits the breakdown. It inhibits proteolysis. However, if a muscle has become insulin resistant, now insulin is less capable of defending that muscle protein. So at any moment, the person will have a higher degree of proteolysis. So at any moment, they're breaking down muscle protein more than insulin would want them to. This is one of the reasons why people with type 2 diabetes and insulin resistance have higher levels of branched chain amino acids in their plasma, in their blood. There's a lot of mistaken directionality here, and the paradigms get a little bizarre. But you don't have to look hard to find substantial evidence that branched chain amino acids are a signal of type 2 diabetes and insulin resistance in the blood. It's not that the branched chain amino acids are causing the insulin resistance. No, they're a consequence of the insulin resistance at the muscle. They are the evidence that insulin is no longer capable of inhibiting proteolysis. Thus, at any point, the muscle is breaking down more protein than it should be, ultimately contributing to a greater sarcopenia. All right, I hope that thought is clear. Now, earlier I'd mentioned inflammation in the study from the Drummond lab at the University of Utah, and I co-authored that with them. I was a collaborator on that study. When we think of insulin resistance, you'll recall that one of the cardinal causes of insulin resistance, one of the three primary causes, is inflammation. And where does that inflammation come from? Well, it often is coming from hypertrophic fat cells. Just as a reminder, when a fat cell has undergone significant hypertrophy, and a fat cell can grow unlike any cell, we wish muscle cells could expand the 20 times volumetric increase that a fat cell can. There's no cell that can grow like a fat cell can, much to our collective chagrin. When a fat cell has undergone such substantial hypertrophy, it begins to become hypoxic. It has pushed itself too far from capillaries, from the life-giving blood vessels of the capillary. And thus, in its hypoxia, it starts to release all of these pro-inflammatory cytokines, some of which will be like breadcrumbs as they're floating towards the capillary. When the capillary senses some of these cytokines, it will start to grow a new capillary out towards this starving or suffocating fat cell. Hypoxia is basically just the suffocating cell. And so that's how the hypertrophic fat cell is trying to correct its own hypoxia or suffocation. But in the process, as it's belching all of these pro-inflammatory cytokines into the blood, you have an increased inflammation systemically, or the entire body has this subtle yet relevant increase in inflammation. This affects mTOR. You've heard of mTOR now, and that is a topic of its own for another time. But mTOR is a primary anabolic signal that can promote muscle growth and inhibit proteolysis. Somewhat reflective, indeed, insulin influences mTOR, no surprise. Amino acids do too, no surprise. But when cytokines are up, like TNF alpha or interleukin 1 beta, both of which come from hypertrophic fat cells, they inhibit mTOR. And if you inhibit mTOR, you are inhibiting muscle protein synthesis. So independent of insulin resistance, we have the overall metabolic milieu with the inflammation coming from the hypertrophic fat cell that is independently contributing to further sarcopenia. And why does all of this matter? Remember, if you start losing muscle mass, you start losing your greatest metabolic advantage. Muscle acts as a tremendous metabolic buffer to pull in glucose and help blood glucose remain at a stable level. And insofar as glucose is the primary push for insulin, if you can keep your glucose normal, it's much more likely you'll keep your insulin normal. Okay, now let's flip the paradigm. As I'd mentioned here, the directionality it goes both ways. And we just got done discussing how insulin resistance affects sarcopenic obesity. And now let's flip it and talk about how sarcopenic obesity promotes insulin resistance. In fact, before I do so, I talked about how insulin resistance contributes to sarcopenia through both the failure of insulin to inhibit proteolysis and the inflammation of the hypertrophic fat cell, compromising muscle protein synthesis. But let's just, before we move on entirely, remind you that insulin resistance is a problem of hyperinsulinemia. And high insulin promotes fat cell growth. It promotes hypertrophy. This is, in my view, it's beyond debate. The evidence is so substantial. There are studies that explore the fat cell size in people who are insulin dependent. So people who are injecting insulin through a needle, if you look at the site of the insulin injection, compare it to just the fat cells just a few inches away. So if a person's injecting insulin in the fat cells right here, you take a biopsy, a needle biopsy, and look at the size of those fat cells and compare it to fat cells just a couple inches over. Let's say it's same belly fat, but it's not a site that the person has been injecting the insulin. The insulin cells here are about 10 times larger than the fat cells just a couple inches or even a couple centimeters away. So insulin has a profound effect at promoting fat cell growth. And as a reminder, even in a diabetic, too much insulin is a key driver of insulin resistance. And part of this is because of what's happening at the fat cell. But insofar as we're talking about sarcopenic obesity, the higher insulin gets, the more the body wants to store energy as fat. So now we have the insulin resistance also contributing to the obesity part of this. And that's because of the elevated insulin of insulin resistance, whereas the sarcopenia and the altered muscle protein status is a result of the failure of insulin to work. Okay, now let's actually flip the paradigm and talk about how sarcopenic obesity contributes to insulin resistance. So some of this is going to be obvious because I've already been touching on it. But if a person let's imagine a person developed sarcopenic obesity through a different pathology. Maybe it was a consequence of some chemotherapy that they were on, or the wasting that comes from cancer, combined with some horrific diet, whatever it may be. Let's just say the person comes to this scenario with the sarcopenic obesity prior. Well, the first problem is obviously the reduced muscle mass. That with less muscle mass comes a vastly compromised ability to control blood glucose. With that comes chronically elevated insulin, and that is, of course, going to be contributing to insulin resistance. So the loss of muscle contributes to insulin resistance. Also, we have the increased fat mass. If a person is developing obesity and the fat cells are growing, which happens when there are two conditions met, namely elevated insulin and to fuel the growth, or to stimulate, we have, if fat cells are growing, it's because of two things: elevated insulin to signal the growth of the fat cell, and then sufficient calories to fuel the growth of the fat cell. This is something I've already discussed previously. Just to really make it clear, you could eat all the calories you wanted, or you could possibly shove in your mouth, and if insulin is low, you cannot store it as fat. The evidence for this is we need look no further than a person with type 1 diabetes. They can eat thousands of calories a day, and if they simply underdose their insulin, they will not gain a single speck of fat. This is one of the primary reasons why I'm such a defender of the endocrine theory of obesity, the relevance of insulin, because if you remove that one single variable, no other variable matters. You want to talk about thyroid hormone, you want to talk about cortisol, you want to talk about ACP and any other signal, it doesn't matter. You literally just remove the insulin and they cannot get fat under any circumstances. Okay, now still, let's come back to this directionality that I've posed, which is the effects of sarcopenic obesity on insulin resistance. So with the loss of muscle mass comes the loss of the main insulin responsive glucose handling tissue. With the obesity is the hypertrophic fat cell, and how the hypertrophic fat cell not only becomes insulin resistant to check its own growth or to slow down its own growth, but also it becomes pro-inflammatory. And I already mentioned the influence of the inflammatory cytokines on muscle earlier. So that is once again directly affecting the muscle. But also with the sarcopenic obesity, the loss of the muscle and the expansion of the fat cells, we have a pretty relevant and profound change in hormones. Muscle, for example, releases hormones that help keep body fat in check, like a hormone called FGF21 or a hormone called irisin. Both of those are muscle-derived hormones called myokines that act to increase fat burning. At the same time, there are hormones from the small healthy fat cells like adiponectin that improve insulin sensitivity throughout the body. But as the fat cell gets bigger and bigger, adiponectin production goes ever further down. So collectively, the sarcopenic obesity ends up shifting hormone production in such a way to further promote ever greater insulin resistance. All right, now, so what about sarcopenic obesity? Well, I don't have to explain to you the consequences. They're pretty obvious now. Once you appreciate that sarcopenic obesity is causing insulin resistance or contributing to it, then we quickly get to all of these plagues of prosperity that I've talked about before, and indeed why I wrote my initial book, Why We Get Sick. Heart disease, Alzheimer's disease, fatty liver disease, infertility, hypertension, all of those and many, many more are directly impacted by insulin resistance. Also, of course, we have the simple reality that the fatter we get and the weaker we get, the more likely we are to have a vastly reduced quality of life. Mobility drops. That results in an overall reduced quality of life and a greater economic burden on the individual or taxpayers at a country or societal level. But the quality of life, I would argue, is the most relevant. A person's just going to be miserable because they have a harder time just living life now. Okay, now, is there any good news here? Of course, there always is when it comes to metabolism, because there's always something that can be done. And it's not a drug. It's not going to be some clever new mix of some pharmacological cocktail. It's going to be, what are you putting in your mouth and what are you doing with your time? But the question is not so obvious, because if we follow the traditional advice of eat less, exercise more, we're simply going to be promoting a caloric deficit. And as I have stated before in previous episodes, the further we push ourselves into a deliberate caloric deficit, the hungrier we get. And hunger always wins. So how can we starve the fat while feeding the muscle? Well, to do so, we cannot have this strategy starting or focused on cutting calories. If we just focus on cutting calories, we end up with a result that's going to be just like what happens on people with Ozempic and Wegovy. When people are taking these GLP-1 medications, they stop eating. And up to 40% of the weight that they lose is coming from their lean mass. Well, if you are already sarcopenic and obese, sure, you want to lose the fat mass. You don't have lean mass to spare. So that would be catastrophic. So we cannot focus on just stopping eating. We need to focus on reducing insulin. When we reduce insulin, but let the calories be what they will, control carbohydrates, prioritize protein, don't fear fat. Those are the three pillars of reducing insulin and losing weight. When insulin comes down, metabolic rate goes up. Remember, now, I'm not saying calories don't matter. Don't ever think I'm saying that. I'm just saying that if you have these two variables to mess around with, insulin and calories, don't worry about the calories. They're going to take care of themselves, in particular for two reasons. One, as insulin goes down, metabolic rate goes up by several hundred calories per day. David Ludwig has found this. There's multiple papers published on this. Part of the mechanism also is going to be the production of ketones. Not only do ketones also contribute to the elevated metabolic rate by increasing a phenomenon referred to as mitochondrial uncoupling. Look at the link in the show notes for a paper from my own lab. We've published several papers on this phenomenon. So ketones increase metabolic rate by just telling the body to waste energy. But even the ketones themselves become wasted energy. As you are breathing out the ketones or urinating out the ketones, each ketone has a caloric value roughly comparable to glucose. And think about it. Every ketone that you're dumping from your body is calories that didn't need to be stored, that didn't need to be burned through exercise. You're just wasting them. So just to highlight a couple papers, we have Volek et al. In 2002. This looked at a low-carb diet and compared it with a normal diet, a low-fat diet rather, low-calorie, low-fat diet, and found that the participants on the low-carb or the insulin-lowering diet lost more fat mass and retained more lean mass compared to those on the low-fat diet. Hallberg et al., 2018, same findings. The group that had a dietary change that was not focused on calories, but focused on cutting carbs and lowering insulin while keeping protein and fat as abundant as the people wanted, once again had greater fat loss and a greater retention of muscle mass. And many people want to think that you can't lose fat without losing muscle. That just is not true. There is a way to spare that muscle. If you lower insulin while keeping calories adequate to fuel muscle, then you are starving the fat cell. The lower insulin gets, the more impossible it becomes to keep fat cells. Brem et al. 2003, same results. Brinkworth et al. 2009, same results. The collective finding from all of these papers and more is that if you focus on reducing insulin, let the calories be what they will, you will selectively be burning fat while retaining muscle. So that's the solution to sarcopenic obesity. Of course, underlying all of this is the fact that you must challenge your muscles. As much as you are, with everything I just said, putting your muscles in a place nutritionally to be preserved because they're not starving, then you have to still challenge the muscle. And my simple recommendation, you're wondering, well, then what's the best exercise? The one you will do. If there's something that you will get up and do it. And minute for minute, the more you are capable of engaging in some resistance exercise, do that instead. So if you have the time to do some push-ups or sitting against a wall with your knees bent to do wall squats, do those. Minute for minute, that will yield a better metabolic improvement, a better insulin sensitivity than a comparable aerobic activity will. So as much as you can, focus on some resistance. But at the end of the day, the best exercise is the one you'll do.